Now that we've looked at how diffie-qs can be solved graphically or geometrically, we also want to take a look at how we can solve them analytically. So when you're dealing with diffie-qs from an analytical point of view, in other words, we're given equations and we're working just with those equations, not with the slope fields, then there's two ways that the test writers tend to talk about things. One is they want you to write a differential equation. All right, so they give you the information, and then based off of that information, you have to write the equation. And the other is that they give you the equation and you have to solve it. So we're going to start by looking at how to write a differential equation. Right. And the first thing that you want to be aware of that the test writers love is that they like to involve the differential equation where you see that the derivative is equal to k, which is some coefficient, times the original function. All right, so dy dt equals k times y. So as we're deriving, we often derive with respect to time, not always, but if we're dealing with population or temperature, it tends to be over time. And what we see here is that the derivative is equal to the original function times another number. So we have to go back into our prior knowledge and think about what function derived to itself. What function was its own derivative? So you're probably thinking, okay, I remember this. I know that e derives to itself, okay? If y is equal to e to the x, well then dy dx, that was also e to the x, okay? And that's what they're talking about when they give you this function. When they're talking about a dy dt equals ky, they are telling you that y involves e to the x or e to the t. And there just might be a coefficient, because remember, also coefficients move from the function down into the derivative. So let me change this ever so slightly. If we had y was equal to 2 e to the x, well, the 2 is a coefficient, so it moves down into the derivative, and then e derives to itself. So once again, the derivative of 2e to the x is itself. That 2 matches with this k right here. K is that coefficient, all right? The y is the e to the x or e to the t part, right? So if you're presented with a situation where they're talking about this, all right, just understand immediately that we're dealing with an exponential function. We're dealing with y equals e to the x or y equals k e to the x, where k is any constant multiple. Right? Next up, they might talk about directly proportional. You discussed this and inversely proportional way back in Algebra 1. Right? If a function is directly proportional, then that means that there is a coefficient, and that's it. In other words, it's y equals k times x. That's a directly proportional relationship. Okay, there's just a constant multiple. There's no plus 2 or anything like that at the end. So it's similar to y equals mx plus b, but it's not the same thing because you don't want the plus b part. You just want the slope and the two variables, and that's it. So if we're talking about writing an equation where something is directly proportional to something else, it's basically item 1 equals k times item 2. Okay, and then inversely proportional, that is just going to be y equals k over x. All right. It's not multiplying the k and the x, it's dividing k by x. All right, so those are the just 3 things for the setup. We'll start to use them in the examples in the next video.